morning, everyone. My name is Prasanna Balaprakash. I'm a computer scientist at Math and Computer Science Division and Leadership Computing Facility. And first of all, thank you very much for coming. Saturday morning, I know it's very hard. Let me see if I can make your time worth. Today, so the first talk is going to be an overview of machine learning methods. Okay, some acknowledgments, and I have prepared this course from a number of online materials. You will see the link there. So let's get into machine learning. So machine learning, right? So as a field, it came or born from the ambitious goal of artificial intelligence. It's not new. It was there from 1950s, 1960s. To begin with, there was two historically different approaches. First being symbolic programming, which is pretty mainstream in 1950s, 60s, where it is sort of mind-inspired. What does it mean? So the scientists and researchers try to sort of understand intelligence from a mind perspective and try to encapsulate all the knowledge in a set of rules for a particular domain, and they write code to capture that. So it is more like a top-down approach and set of rules that try to solve a problem using logic. On the other hand, machine learning, which is gaining a lot of traction in the recent years, takes a completely different approach. It's a bottom-up approach, or a brain-inspired approach, where you don't explicitly try to capture the knowledge or capture the intelligence, but you give a lot of data. You give a lot of training data, and you develop algorithms that can learn from the data. Okay? So that will eventually give us sort of programs that can solve problems later on. Okay, so that is the key idea behind machine learning. Okay, so there is another way to look at it. So machine learning is sort of it gives the computers the ability to learn without being explicitly programmed. So far, in the training program, what you might have seen is the traditional programming, right? So you start with the data and program, and then you scale it up on a big machine, and you get an output that is the answer to your problem. Okay. On the other hand, machine learning takes a different route. It takes a different path. You give abundant data, so that is the key. You have to give a lot of data and the output. Okay, so you give examples of the solution to the problem, and then use machine learning algorithms on large-scale machines to get the program itself, which you will use to solve other similar problems. Okay. So machine learning is not a single discipline per se. If you look at it, it takes inspiration from different branches. For example, statistical physics, statistics, information theory, optimization and control, and a lot of neurosciences too. So the field is evolving quite rapidly. And it is a double-edged sword, right? So on the one hand, you have to keep track of what the new things happening in the field. On the other hand, it is progressing so rapidly that the whole field of artificial intelligence is gaining a lot of traction in the recent years. In the popular media, right? So you have seen artificial intelligence, machine learning, deep learning, all these terminologies have been used, one way or the other. And I want you to take a note at, so what this all means. So artificial intelligence is a sort of a very broad field, or a very broad area. Machine learning is currently a promising approach towards artificial intelligence. It's a set of algorithms, ideas in which we develop frameworks, develop solutions to achieve artificial intelligence. Deep learning is a class of machine learning. It's a neural network approach, primarily inspired by the way that human brain process information. And deep neural networks, it is the sort of the heart within the deep learning. So this is the sort of hierarchy, and this has been used in different ways, and we will follow this sort of approach. So when I talk to domain scientists, so a lot of times I have to sort of bring down the expectations because one promise is that, oh, machine learning is a magic. It's going to solve all your problems. That is not true. So machine learning is more, it's not a magic. It's more like gardening, okay? The seeds are the machine learning algorithms. The nutrients are the data. And the gardener is, of course, you. You have to put down everything together in the right way to grow that plant. The plant are the programs that come out of the machine learning project or exercise that you are going to do. So in machine learning, we use a lot of examples as a training data. If there is no such concept of examples in your domain, you have to think about how to develop those examples, or how to formulate your problem in such a way that I have list of examples which I can feed that to the program. Okay? Ideally, many examples. You cannot do machine learning with 10 examples. Okay? So you need a lot of examples. Preferably with each example being a vector, which we will see. Not necessarily. So even you can deal with big image data sets, but eventually you will turn that into a vector. Okay. So there are different sub-topics within machine learning. Okay. So what you see here is sort of the major pillars of machine learning. Starting from supervised learning, which we will cover this morning, and then to unsupervised learning. So supervised learning is typically how we learn from our parents, our teachers, our mentors. So we need some sort of training to do something, right? So that is supervised learning. Unsupervised learning is something, okay, we have some knowledge and we go and generalize that to a new domain, right? So that is, you do things or you learn things without any supervision. So that is unsupervised learning. Semi-supervised learning is a mix of supervised and unsupervised. And reinforcement learning, finally, is a different class of approach where an agent interacts with an environment and try to learn from the interaction. Okay? So let's first focus on supervised learning. A typical workflow for supervised learning looks as shown in the figure. So it has two distinct phases, okay? A training phase and a testing phase. The training phase, you have, let's focus on images, okay? So you have images, set of images, and labels. So let's say you have set of images, and the labels are cats, dogs, humans. And you go and do a feature extractor. So you extract features from that image, and as a result, you will have the features, and you give that to the machine learning algorithm. And then you give the labels to the machine learning algorithm. Okay? Now the algorithm will try to learn the relationship between the features and the labels. Okay? And then it will result in a so-called trained classifier. Okay? Now this is a code, this is a program that is produced by this algorithm. And in the testing phase, given this image, the feature extractor, you extract those features, you send it to the trained classifier, and it will give you the label. Okay? Okay, so how we actually do this, right? So there are several things happening in this slide. Okay, so I'm going to go one by one. So given an image, right? So a set of images we called number of examples, a small n. And the training data set, the training data set is composed of set of images and the target labels. Okay? And we take these images, do pre-processing, feature extraction, and convert that into vectors. So if you remember, this is what I mean. We usually deal with vectors, or consider this as a matrix. Okay? So we always deal with this sort of matrices. Okay? So in the matrix, what you see is each row is this is a vector that corresponds to this image, and this vector has values that are extracted from this feature extraction process. In worst case, you can just take the pixel values and put them directly there. Okay? And then the target labels being +1, -1. You can do some sort of encoding to make it +1, -1, or 1 or 0. So this is the training data set that we will work on. Okay? So we will give this to the training example, to the machine learning algorithm, and then we will ask, given a new image, what the label of this new image is. Okay? So what happens actually is, okay, so for the sake of illustration, let's consider this two-dimensional example. Okay, so we take this matrix, and then we have this target labels, and we map that into this two-dimension, and let's say the blue labels are cat and the red labels are horses. Okay, so now we want to build a classifier. So the classifier tried to build some sort of separation. Okay, so this is one possible separation, right? This is another possible separation, right? And this is another possible separation. And the new horse image that we gave is basically sitting here. So given these three different types of classifiers, right, which is the best one, right? So the third one is sort of better than the other two, because from the training example, there is only one misclassification. It can find this boundary, nice separation, given this new testing image that basically belongs to this red cluster, and it says, okay, I'm going to classify this as a horse. Okay, so this is when the output values are labels. It doesn't assume any numerical values. Then the problem is called classification problem. Okay. Regression problem is very similar to classification problem. The set of algorithms, there are a common set of algorithms that you can use for classification and regression. The only difference is your target is not anymore categories or labels. Your target is numerical values. Okay? So you take those numerical values. So for example, this is again for illustration. Let's take 1D example, and we want, these are the training examples. The yellow points are the training examples, and we want to find, given a new x value, what is the corresponding y value. So again, given this one, we can fit different types of models, and the best model depends on the algorithm, depends on the data. So we take that best algorithm and then ask, okay, so if this is, if the red is a model that is produced by the algorithm, then we will ask what is the value of this point here, and then we project it to the y. Okay? So if you think about supervised learning, so the general framework, there are three key elements. First one, function family. The function family is often determined by the algorithm that you choose. There are different types of algorithms, and depending on the choice of your algorithm, you limit the function family. The loss function is basically a measure of how much your model is, how much you are, during the training process, how much your model is mispredicting the label or the numeric output values. So you will have the input x, the target y, the function family is f of theta, and you want to find the best theta for the given training data set. So given any values of theta, you can get the output, right, f theta of x, right? And then you can compare that f theta of x with the target value y, and the measure of this difference between f theta of x and y is the loss function. So that is the second component. The third component is the search for the best function, right? So now you know any value of theta will produce some value of f theta of x, but eventually you want to reduce this loss function, right? So you can formulate this as a mathematical optimization problem and then solve it using some optimization algorithms, for example, stochastic gradient descent. So here is the key concept behind any supervised learning algorithm. So there are different classes of supervised algorithms, and they exist for a reason, because there is no single algorithm that can perform well on all data types or different data types. So you have to find the right set of algorithm for the right set of algorithm for the given data. Okay. So what you see here is the key idea behind supervised learning, which is bias variance trade-off. So what does it mean? Let's say you are given with the data, right? A set of inputs and the corresponding outputs. And there exists a function f star that is the best function that can model the relationship between f and the input and the output. Okay? If you choose an algorithm, the set of all possible functions that particular machine learning algorithm can explore is shown as this blue curve. Okay? You start from f hat. Okay? You initialize the algorithm, you initialize the training process, you start with the algorithm, and then you start here. So the best function that you can find is f star. Okay? So given this blue, the best function that is closest to f star is this one. So eventually you have to reach there. Okay? So the distance between what you currently have and the best function f star is called the variance. Okay? So if you have large variance, so what does it mean, variance? If you don't have enough data, or if you are not learning well from your from the given training data, the distance between the best function that you can possibly learn and the function that you are currently having is called the variance. So if you have variance, then basically if you are in this regime like high variance, your predictions will not be precise, right? But once you learn, right, let's say you reach here, that's the best function you can possibly do with that particular algorithm. If you do that, then the distance between that function and the best possible function that can model the data is called bias. Okay? So the bias basically determines if your given data set is the functional relationship between the input and the output in your given data set is too complex. And if you choose a simple algorithm, let's say linear model, you cannot do that. You cannot model that, right? So that distance is called bias. And that is this one. So that is the approximation error. So even if you can learn the best you can do with your algorithm on your training data, but your original function that you have to learn is far away, then you have to go for a bigger algorithm. The reason why currently the deep learning algorithms are much more powerful than all other so-called shallow learning algorithms is because this blue region is so big. It's quite big for deep learning. For all other algorithms, it's sort of limited. So that's the reason it can potentially model any sort of functional relationship, but then you need a lot of training data, and you have to optimize the parameters. So this distance is large. So when this blue curve when the blue region is quite big, then this distance is large, and you need to find, minimize both of them. So that's one key idea that you need to remember when you are applying supervised learning. Okay, so unsupervised learning, it is primarily used as a sort of a subsidiary procedures for supervised learning on a number of cases. So this is an example of clustering. So given a data set, you don't have a particular target to predict. What you want to do is, in the case of clustering, you want to organize the data into some sort of clusters. You define the distance metric, and then you see, oh, is there any sort of cluster that is available in my current data set? Often, you generate data from physical process, and the physical process have some sort of correlation, and you want to sort of understand what those correlations are. So this is a small cartoon on this clustering. You start from there, and this is a k-means clustering. and you start from some random points, and you iteratively improve the quality of the clusters. Okay? Dimension reduction is another popular approach where, if your input dimensions are quite big, then what you end up is, you're learning. It's quite hard to learn from that very high dimension. Okay, so one way to reduce those dimensions is dimension reduction techniques, and a sort of a popular approach is a principal component analysis. Basically, this is a two-dimensional data. Given this sort of data, you see there is only one dimension where the variance of the data is quite large, and in this dimension the variance is quite small. So we can basically compute the principal component and then use only one dimension to represent two-dimensional data. Okay, so for the illustration in two-dimension, it doesn't look really impressive, but when you are doing it on 100 dimensions, and if you can reduce these dimensions to 10, your learning will be much faster, and you don't need a lot of training data for that. So this is a new class of unsupervised learning that is coming up in the context of deep learning called generative adversarial networks. So the idea is quite interesting, and the approach is very cool. So you have two neural networks, which is, often this is explained in the terms of a generator, a detective, who is trying to detect the real data from a fake data which is produced by a forger. Okay, so if you keep on giving this data, the detective will sort of, you give the labels and you say the detective will detect which is real and fake. But if you take the feedback from the detective and give it back to the forger, like how this detective is detecting the real from the fake, then this guy, the forger, will start producing realistic-looking data. That is, realistic-looking pictures. Okay, so what it entails is you give any sort of data, then you can capture the distribution. Okay, if you give a bunch of numerical data, computing the distribution is quite straightforward, right? You can compute the you can compute the histograms and then try to fit the parameters of the distribution. How about if you give images, right? You give real-world images, and now I want to compute the distribution of these real-world images. And once I compute the distribution, I can sample from the distribution so that I can synthetically produce realistic-looking images. Okay, so the generator and the detector are two neural networks. They are basically fighting against one another. One guy trying to outsmart the other guy, saying that, okay, this is from the real, or this is from this fake generator neural network. And then the fake neural network will try to learn how this detector is detecting and try to produce realistic-looking data. So this is the output from that realistic-looking data, where you are given with a sort of a benchmark data set of realistic images, and then this is a cluster of bedroom pictures. Okay, so these are bedroom-like pictures. If you really look at each of this picture, it has a bedroom-like characteristics, but they are synthetically produced by neural networks. But we didn't say these are bedroom pictures, these are living room pictures, these are library pictures. We just gave it to the network and asked the generator to learn to produce realistic-looking images. And this is how it started producing realistic-looking images. Okay, so I really like this approach because this is one way. So far, the machine learning algorithms are sort of number crunching algorithms, right? This is one way to sort of make deep neural net understand how our real world is made of. Because our world, our vision, when we look at the world, it's often have sort of characteristics, features, symmetry, right? We don't see random pixels, right? So our world is made up of building blocks. So this is one way to teach neural network how our world is made of. Finally, reinforcement learning. This approach has received a lot of attention, when Google DeepMind's devised reinforcement learning based approach, and it sort of beat the world champion in Go. For example, why Go is so important is because compared to chess, Go is much more complicated. It requires you cannot just do branch and bound and find the best move. It needs a lot more human ingenuity to play the game of Go. But what DeepMind has done is just devise this reinforcement learning where an agent tries to interact with an environment and then learns from the reward. And you do this in an iterative fashion. So what they did is they took a lot of games, videos of the games, and give it to the network to learn automatically. You know, the agent tried to play, and based on the reward it gave, it started finding policies which finally can outperform human champions 4-1. So that is this AlphaGo, and after that, this approach started having a lot of traction in the research community. So there's also a lot of application in the robotics where you want to design or develop an agent that can learn and interact with an environment. Okay, so with that, I sort of come to the summary. So there are several different classes of machine learning algorithms. The type of learning algorithm that you have to use depends on the type of data set and depends on the question that you are asking. One way or the other, most of the time you will start with supervised learning, but then you will quickly enter into unsupervised learning. And there are a lot of interesting algorithmic developments happening within both supervised and unsupervised learning, and also reinforcement learning. So with that, I end my first talk, and then we can go to the next talk. Do we have time for questions, Martha? Okay, yeah. Right. Yes?
How much do you guys look at the bias in these training sets in the beginning before you put it in these algorithms?
Manually. So which bias are you talking about? The bias in the bias variance tradeoff, or the bias in the training example? It's
Training example, like say a bunch of some are like it was horses, and I put horses or something like that.
Yeah.
So that creates like a bad.
Yeah. So this is the bias in the training, in the data collection. We see that all the time. Okay. So it's quite rare that the training example is very well balanced. If you take like multiple classes and all these classes are equally distributed, it's not the case. Often we have to come up with different set of algorithms to address the imbalance in the data. So for classification, there is a class of approaches that you can adopt for balancing the data. So one of them I will talk in the next session. There is also a new class of data augmentation algorithms that are coming up. If you think about the unsupervised learning, you can use that, use unsupervised deep neural net to develop data augmentation algorithms, which then you can use to augment your data, to balance your data, and then do the training. Yes?
What kind of solvers do you guys use in your machine learning codes? You use like, stochastic gradient descent or stochastic Newton, and what do you prefer, and what have you seen with those?
Yeah. Okay, so I can talk from deep neural net perspective. It's stochastic gradient descent. People try to use other solvers, but it is so effective. So in the case, so stochastic gradient descent, or the deep neural net powered by stochastic gradient descent is so much work efficient. What does it mean? You take the training examples 20 or 30 times in the stochastic gradient descent, sample them, and then you do operations which is sort of linear in terms of number of parameters in your deep neural net. And the things that you can do just by doing this bunch of matrix multiplications and doing stochastic gradient descent, so amazing that you eventually end up with classifier or even reinforcement learning type of things that completely outperforms human competitors, so to speak. Why that's the case? Because deep neural net, if you think about it, it has thousands of parameters, and there you have to take steps in such a way, using stochastic gradient steps in such a way that you keep on improving the objective function, but you don't want to take really large steps, right? So you don't try to solve the problem in a couple of iterations, because that won't work. One reason being you have large number of data sets. You cannot move all the data set into the single node, and then you try to do the full batch. It was even shown that if you take the full batch and try to do an update with the stochastic gradient descent, your testing error is high. It leads to either overfitting or overgeneralization, and it has several other problems associated with it. So we use stochastic gradient descent, and that sounds pretty amazing. That works. Yeah.
For the generative adversarial network, can your generators start from just like randomly producing examples, or do you need to have like some sort of simple initial model for the generator?
For the generator, so the generator works as follows. It takes a random noise as an input and produces an image. Okay? That image in the beginning, it is just random pixel values. Okay? But then you give that to the detector, and the detector will say, okay, this is a fake image, but you also give, let's say, the real image, even if it is few. Okay? And then what happens is that the detector will say, okay, this is, you classify them, right? So you give the labels. You say this is real and this is fake, and the detector will learn how to differentiate fake from the real. But then when you do back propagation from the generator, you also do that on the, from the detector, you also do that on the generator. So now the generator knows how the detector is detecting, or how the detector is doing this classification, and using the negative gradient of that, now the generator will adjust its parameters to produce realistic looking images.